So these are the topics I will be covering today, which are what is an assembly language, why should you learn assembly language, and then after we learn what's an assembly language and why we should learn it, we'll start diving in what's in the CPU, and because assembly language is a programming language that is designed for CPUs, we're going to look at what's inside the CPU, and we're trying to understand what it is, how it's working, and how to use them. So in that category, we're going to look at what are registers, what are memory segments, and we're going to learn some basic instructions, build some very basic programs with them. Then we will learn how to do the control flow and loops and functions. Then I'll teach you how to make the proper way of the calling conventions, how to make properly call and write functions. And then we're going to go over 2 example programs, and then we'll end it with a simple Q&A session. Oh, okay, I can wait a bit. Alright, I'll be waiting for it. So, I should probably first listen to these ones. Okay, I'll go over these once again when people joins. I'm sorry, I'm using only one monitor right now, so it's a bit tricky to understand all of this. And this is my first presentation here, and I didn't have too much time to do all of this, so I'm a little bit nervous. Hello to all of you. We'll be starting in a few minutes, like in a minute or two. Hello. Have we become right? Yeah, okay. Let's see, I'm just gonna start right at the clock, 7 p.m. UTC. Alright, so we're going to cover 5 topics for today, not topics, but subcategories. And first one is, what's an assembly language? We should know what something is before learning it. So, and then why you should learn assembly, why shouldn't, where it is used, why you should learn it, I'm just repeating myself, sorry. And then after we're learning what those are, we'll go, since the assembly language is a language that's so close to CPU, we're gonna go and see what the CPU in your computer has, and we have to learn what those are to understand how to use the language. So our other topic will be what are registers, then what are memory segments. Those are the 2 things that we will be covering inside our computer, and then we'll be moving on to some basic instructions, and with those basic instructions we'll build some small programs, really simple, really small programs, and then I'll show you how to make control flow, comparisons, loops, and functions. And then with the calling convention, I will teach you how to make and call functions properly. And then we'll write a couple of example programs, and after that it will be followed by a simple Q&A session that I will take from the Twitch chat and Discord chat. So let's start. What is an assembly language? In computer programming, a assembly language, sometimes abbreviated as ASM, is any low-level programming language in which there's a very strong correspondence between the instructions in the language and the architecture's machine code instructions. This is the Wikipedia definition, which may not be the clearest definition of all. So, and let's say we have this machine code here. What is machine code? In computer programming, machine code is a low-level programming language consisting of machine language instructions used to control a computer sensor processing unit or CPU, or same. So, in other words, or simpler words, an assembly language is human-readable binary code. Like, we will tell the CPU to what exactly which instructions it will execute, and it will do them, basically. So it's a very low-level language. It will be hard to write because we have to do everything by hand. So why we should learn it in the first place? Assembly language doesn't have much use in the industry itself, but it will help you understand other stuff. Like, when you're writing a C program and you wonder why something is like that, or why it doesn't work, why it should work, but it shouldn't work, basically almost all the time the answer is lying under knowing assembly language. Because the assembly language is a simple language, and it's basically simple CPU instructions. When you write C, and C is just a sugar coating over assembly language, it will do this thing that will be most easily transferable to assembly language. Maybe not the most easily, but you get the basic idea. Learning assembly can actually make you a better C and C++ programmer, because you will be learning about the CPU and how it works, and knowing how it works will help you understand how to optimize your code, first of all. Like, if you didn't know what some instruction existed, you could go around the way, but if you know that instruction exists and you can use it, you can make a better program with it, a faster program with it. You can predict what some function will do. You can predict what your program will actually do when you know assembly. It can also help you understand how it behaves under how C and C++ behave under some circumstances, and why it behaves like that. So when you have this in the server or in the other places, we get a lot of questions like, why I can't access this variable here from this function? If you know if assembly, you would know answer to those kinds of questions. If you understand assembly, you're gonna understand how things work in a lower level, so you can correlate with those concepts with the higher level languages more easily. And lastly, in some circumstances, you will need to write assembly. There's basically no escape, or there's no better way to do some stuff. Like when you're writing a BIOS, a UEFI, a bootloader, or writing some parts of your kernel operating systems. In those most kernels and operating systems usually use a higher level language like C, but you always need to know assembly to write them effectively. I don't think anyone could ever write a kernel or a bootloader without knowing any assembly. Another reason could be that writing an optimized algorithm. Some instructions that are supported by CPUs can be used, but okay, that's not a good definition. There's some kinds of way to optimize algorithms that you can't just do in higher level languages or compiler cannot detect. There's also an option to program microcontrollers that don't have any good compilers. So I do a lot of microcontroller stuff, and there are some chips from China that I buy, which are really simple, They're cheap, but there's no compiler available. There, you only get the assembler. And in those kinds of circumstances, you don't have to actually learn the whole assembly language. If you know the assembly language, you can always translate to the other architecture's assembly language and program that very easily, even if you don't have a compiler to that. And there's also the parts when you want your direct control over your hardware. What that means is when you want your CPU to do exactly what you tell it to do. In those circumstances, you would need assembly language. It doesn't have that much use as a bare language in industry. Only like computer engineers and stuff use them. But for learning assembly will make you a better programmer in general. So let's go. Since we're going to control the CPU, let's take a look at what is actually inside a CPU. First of all, registers. The registers are a small, let's read the Wikipedia definition. A processor register is a quickly accessible location available to a computer's processors, which means that it's like RAM. It's just that it's very small and it's on the CPU itself, not on another memory stick, and it's extremely fast compared to the memory. Accesses to these registers are almost instantly. That's why you probably want your data in your registers. If you put your data in registers, it will be much faster to do operations with them, do calculations with them. And in assembly, we mostly use registers to do, like, most of the stuff we do isn't or correlated with registers because they're a very fundamental part of CPU. So there are two kinds of registers: a general purpose register and a system register. General purpose register is the one we're going to use in today's programs. These are the registers that store temporary data on the CPU and used by programmer for various purposes. Like when you want to do anything basically that's outside of memory, like you don't want something done at memory, to do some operations on something that is not on memory, as I said it before, but I'll say it again, you will do it on GPRs. Except for floating point, but we'll get to that later. And so these are basically your basic toolkit available. Not toolkit, but basic tools. Not tools, sorry. Basics, like, this is the stuff that you do operations with. And in general, if you have more general purpose registers in a CPU, it would be faster at doing certain/most tasks. Because processor wouldn't need to swap in that data in the memory to registers when doing operations. Let's say you want to add 500 bytes. Loading each one of them up to 2 registers and adding them would be slow, but if you can keep 10 of them or 12 of them in registers, it will be faster. Or you can just, like, if when doing a complex calculation, you can just store the result of one in another register instead of into the memory, which would increase the speed of the program by a lot. Most processor architectures have different number of registers, like AVR has 32, ARM has varies different depending on the ARM version. But the architecture we're going to cover today, which is x86-64, has 16 general purpose registers. And there's also system registers, which we won't touch today, but those registers are used by your operating system. Those use the interrupts, descriptors, anything that is done by your operating system is done with system registers. And since we're not going to do any operating system development today, we're going to stick with the general purpose registers. So let's take a look at the general purpose registers on x86-64. There are 16 one of them, as I said. There is RIX, RBX, RCX, RDX, RBP, RSI, RDI, RSP, R8 to R15, basically. These are all the registers that are available to you, and all of them are 8 bytes in size. So each one of these is 64 bits or 8 bytes. And lower 32 bits of these registers can be accessed as EAX, EBX, ECX, EDX, EBP, ESI, EDI, ESP, R8D to R15D. So we basically replace R with A, and it will become a 32-bit register. It acts as a 32-bit register, and you basically suffix them with D on the R registers. And then lower 16 bits of these registers can be accessed as AX, BX, CX, DX, BB, SIDI, SP, R8W to R15W. So basically you don't have any prefixes like E and R. The lower 8 bits of registers can be accessed as AL, BL, CL, DL, SIL, DIL, BPL, SPL, R8B to R15B. And there's the bits 8 through 15 of some registers, which is byte 2, can be accessed as AH, BH, CH, and DH. So, you might be wondering what are those D, W, and B are coming from, and that stands for byte, word, double word. And also keep in mind R8 to R15 are not accessible in 32-bit assembly. So this is a basic representation of how they look like. This only covers up to like 11th register R11, but all the others are same. There's this. Every register has one of these. Like it's RAX. The lower 32 is our EAX. Because it's in a little Indian order, it looks like this. There's AX, then AH, and AL, looking like this. As you see, you can't access the second byte of these registers. This is how it looks like. And there is some special purpose of the two of the registers we have. There's RBP. This is a register that holds a point to the base of the current stack frame. And the RSP is the register that holds a point to the top of current stack frame. So these are actually not has to be this way, but that's like the way to go with these, because these mean special things to special things. These only wouldn't mean the stack pointers if you were doing some weird stuff in bare metal, I think. I don't know if there's any other uses that you can use this from, but probably not. I have never seen any. So, as we said, what is stack exactly? In computer science, a stack is an abstract data type that serves as a collection of elements with two main principal operations: push, which adds an element to the collection, and pop, which removes the most recently added element that was not yet removed. So it's basically like, I like thinking of it as stacking up books. You put a book, you put one more up on it, you put one more up on it, you pop the other one. You can only add to the top of it or remove the top one. And in assembly, when you call a function, it will operate its own variables, its local variables, in its own stack frame. The bottom of that current stack frame is pointed by the RBP, and the top of it will be pointed by RSP. And when you enter the function, RSP and RBP will be aligned to point the same address. Function handles the stack frame itself. Some special instructions like push and pop affect RSP and RBP. The push instruction will increment the RSP, and pop will decrement the RSP, stuff like that. It means basically like adding something on stack and removing something first. It's equivalent for that one. And since we have mentioned the stack, let's talk about what else is on RAM. There are memory sections that we use when coding. So the memory sections are where your code can live, or code or data can live. There is .data section, which is where your computer stores your initialized global variables. Like when you have a global variable named A, and you declare like int A equals 5, that will go on .data section. BSS section, there's also the BSS section, which stands for block sorting symbol, but I think it makes more sense to Oh, sorry, Aspi. Yeah, you're right. But like in terms of like regular uh, push, put something on the stack frame, like it increments the stack itself, the size of the stack. That's what I meant. Sorry about that. If ever caused any confusion. And in BSS section, block starting symbol, or I would rather look at that as better say space, is where your computer puts your uninitialized global data. Like when you declare something like int array, which is an array type of 10, that will go onto the .bss section. And there's also the .code section, and that is the segment that stores the instructions that you execute with your program. Well, basically, when you write some code, it goes into a code section. When you add some variables, they can go into data section, BSS section, or data section, or stack, sorry. There is also heap. This is the part of memory you allocate by hand and free by hand. In C, you use malloc, calloc, realloc, aligned alloc, and free functions to allocate and deallocate space in this section. Here's an example of all data segments, the places where your data can go. So when you declare something like int a equals 5, this a variable will live on the data. And when you do it int b and you don't make it equal to anything, it is uninitialized global variable, it will go into BSS section. Now in the main function, let's say go into a function, it doesn't matter, it's a main function, it can be any function. And when we declare a function like int c equals 4, it will be stored on the stack. And when you do int d will be also on stack. See, when you make a non-global variable, it doesn't care that if it's initialized or not. These all will live in stack. And when we do int pointer e equals malloc size of int, e is on stack, but what it points to is on heap. So it points to somewhere in heap that we will keep the actual int variable. Now, let's talk about some instructions. I will be going over NASM syntax because that's the most widely accepted one and used one, and that's what most people prefer. So in this NASM syntax is instruction, then destination, and then source. What that means is it works like this. Here we say c equals 4, and that's basically a move instruction. Like if something has to be saved, it will go into the destination. That's what I mean. And we calculate addresses, basically dereference pointers, using these square brackets. So move x comma y. The move, I'm going over move and or XOR, add, subtract, inc, and dec. Those are all instructions I will be covering for right now. So when we do move x to x comma y, this is how you do, by the way. You put a comma between operands. These are called operands, and these are called instructions. Let's say x was 1001 and y was 0011. After the instruction, it will take the y value and put that into x, which after the instruction it will be x will be 0011 and y will be 0011. As you see, y doesn't change. There's AND instruction, which is basically logical AND in your programming language like C. If we start with the same initial state again, x equals 1001 and y equals 0011, after the instruction, it will order those two variables, those two values, and put the result in x. As you see, x equals 0001 and y will become 0011. You can do the same with the OR instruction, which is same as logical OR. If you start with the 1001 and y as 0011, x would become 1011 and y won't change. There is also exclusive. Oh wait, did I say logical and OR? Sorry, those are a binary. Sorry. These are binary logical and OR instructions. There is also XOR instruction, which is basically takes x. Let's go into the same example again. If x was 1001 and y was 0111, x would become 111. Alright, 1110, and y would. So I did a typo here. This should be 1. This one here. Sorry about that one. This one here should be a 1. Add instruction adds the two operands together and stores the value in x. If x was 1001 and y was 0011, x would become 1100 and y would become 0011. And subtract x, comma y, x will same thing, and it will subtract y from x and store the value in x. There is also increment, which takes only one operand, and well, basically it's same as add 1. And there's also decrement, which decrements is also equal to subtract 1. So these are the simple instructions, and we're going to write this C function you see here using those. Well, this is not exactly rewriting the function, but it's like it will be similar. So I'm just gonna assume three things here. Let's say that we store A in RDI register and B in RSI register, and let's assume C is stored at RAX register. So we declare a label. This is a label. This basically tells the assembler where the function, where function, or like basically in somewhere to be jumped, somewhere to be like gone will be. So first, we don't want to change the value of A and B when doing any of these instructions. So let's take RDI, which was a variable, and put that to another register. Let's call it RDX, because we're not using that. We are free to use that. So RDX is equal to A after this move instruction. So then we have to OR that with B. Since when we do an OR, the second operand won't change, we can safely do OR RDX, RSI, which will OR and store the value in RDX. So after this instruction, RDX is equal to A or B. And then we're going to do the same with this part of the equation here. We're going to move RDI to RCX this time, because the RDX is full, and we're just looking for another register. It doesn't matter which registers we use. And equal to A, and then subtract the RSI, which is B, from RA, which makes the RCX equal to A minus B. So now let's XOR these RDX and RSI. So RSI would be equal to A or B XOR A minus B. And then we just have to move this last value to C. So we're just going to move RDX to RAX. Now this is basically how we write a simple function in assembly. This is, keep in mind, this is not actually how you write it. We're going to get to that in a few minutes. And let's talk about control flow. When we write our C programs, we usually don't do arithmetic like ORs and X's, XORs, addition, subtraction. We do ifs, else's, loops. How do we do that? To control the flow of the program, we have to use labels. As I showed here, the foo, let's say, this is a label. We can move, or we can change our way of execution to those labels. This is called jumping. There is this register called RIP, which stands for instruction pointer. The IP stands for instruction pointer. It is the register that points to the next instruction to be executed. So let's say if we were here, we execute this. RIP now points to this. And after that points to this instruction executed, it will point to this instruction. And then this instruction, this instruction, this instruction. It will move like that. And we change that instruction, pointer, change that register. We can't directly read or write to it. But we can use some other instructions to change this value, which are mainly jump and call instructions. To jump as a result of a condition, we need to use CMP, which is instruction which stands for comparison instruction. That instruction subtracts two operands and sets some of the flags on CPU accordingly. I'm not gonna go deep in what are flags in the CPU, but just keep in mind that like they're like toggle switches that toggle on depend on specific events, like when the number overflows. So if we do comparison x, comma y, what will, and these are some of the jump instructions that we can use to, after this instruction, to move to somewhere, move to some label, jump to some label. So first one is JMP label, which is unconditional jump. We will just go to wherever we want. Like if you want to make an infinite loop, you can just jump to the label, come back, and then jump to the label again. That will make an infinite loop. Jump equals label is equal to, if x is equal y, isn't push a fancier move? It is not a fancy move. Like, I mean, it kinda is, but no, not really. It does other stuff, like it pushes a value to the stack and then moves it. We'll do the Q&A session later on. You can ask the question there. I'll answer it more deeply. And there is jump not equal then the label, and that will be, this will be how it's done in C. X is not equal to y. JL label if means jump if x is less than y. Jump not less than label, and that's basically not of this. Like I represent them in here. There's jump greater than, if that will jump if x is greater than y. There's jump not greater than, which does this. X is not greater than y. There's jump less than equal to. There's jump not less than equal to. There's jump greater, and there's jump not greater than equal to. Those are the some of the jump instructions that are most of the time useful. So let's write a simple example using those instructions. How about that? So let's take two numbers again. Let's assume a is at, okay, let's first go over the C function. There's an assigned log A, there's an assigned log B. If a is not equal to 0, let's increase the b by 1. So first, let's assume again a is RDI and b is RSI. Those are just the random registers that I choose. It doesn't matter. First of all, we have to, for this comparison, we have to compare RDI, which is a, to 0. And if we are equal, if the jump is equal, we're going to do jump to else label, which I defined here. If a is equal to 0, it will jump to the bottom here. But if it's not, it's going to continue and it's going to increment the RSI, which is what we are doing here. And then there's a no op. I just put it there to show you. There's nothing. And that stands for no operation, which makes no operations. So this is how we write the above function in that was in C in assembly, if we assume A is RDI and B is RSI. So what about functions? Like we go to a function and come back. How can we do that with labels? We can't just put different labels, make different functions every time we want to go back. That would be same as writing code. So, well, there's a trick, not a trick, but there's this thing we use, which is RIP, which is the instruction pointer. And to saving that instruction pointer on somewhere, like stack, most of the time it's used as stack, you can go back to that point after you're done with the function, the subroutine. So when we have a function like this, when you call this function, it will increment the RAX and return, and it will continue moving from here. But how can you do that? We'll take a look at how it works in this way. So when we call, it pushes something, the RIP on stack, and then when we return, it uses that value to take us back to where we were. But first, we will take a small look at the calling convention. And in this, I'm going to show you how we keep track of our variables, our parameters, return addresses, and stuff. All of the stuff. Steam buffering, is it? I don't know. Okay. Okay. Interesting. So, what the calling convention is that it's basically a standard for functions to be written. Well, it basically tells us this function will take its arguments like that. You will call all the functions like this, and that's like basically how you keep the same thing. Sorry, how you keep a constant interface between all the functions, like writing a function assembly and calling it in C, calling a C function in C++, how standard libraries work. All of them are possible because we use these calling conventions. So there are two main calling conventions in x86 64 assembly: Win64 and System-V AMD. Since I will be going over Linux assembly programming on this, and Linux uses System-V calling convention, I'll be going over that. A function cannot change the value of RBP, RBX, R12, R13, R14, and R15. If you want your function to use those registers, you should save those values somewhere and then put those values back in those registers before returning from function. This basically means you have to preserve the values of RBP, RBX, R12, R13, R14, and R15. The value of RBP plus 8 should be multiple of 16 before calling a function. Why do we do that? So there's a how can I explain this? So some data types require some kind of alignment, like local variables. Let's say a long has alignment requirement of 8. And function can just assume that the alignment is made for itself before calling. So it doesn't have to worry about any. It just assumes that if this stack is 16-byte aligned, so it can put its variables there safely. And the parameters that pass in the registers in this order: first parameter in RDI, second one is RSI, third one is RDX, fourth one is RCX, fifth one is R8, and sixth one is R9. We pass them in these order. But what if we have more parameters? In that case, remaining variables are passed on stack on reverse order. What does reverse order means? Let's say we have a function that takes 9 arguments. We put first 6 of these arguments in the registers. Then we go to the 9th argument, push that on stack, then go to the 8th argument, push that on stack, and go to the 7th argument and push that on stack. So we have all of our parameters that can be accessible to the function. After doing all of this, aligning, putting our parameters, the caller executes the call instruction, which is same as push RIP and jump to label. The called function puts RBP on stack because it has to preserve it. This is not actually a requirement, but this is what you do when you need some local variables on the stack. This is the most basic way of doing anything on stack. That's why I added. And called function sets RBP to RSP and then changes RSP to make room for its local variables. And how does this work is, well, I'm going to show you how a stack frame looks like in the next picture, and that will tell us about it. And you will see that the place between RBP and RSP will put our local variables. And to make that, we have to do it like this. And the function executes, clears its own stack frame, then executes ret instruction, which is used to return to the caller function. Which means we're going to do everything, clean up our own mess, and then go back. So this is how a stack frame looks like. So this is our RBP at call. This is RBP at the moment of call. And as you see, RBP plus 8, this place should be aligned as 16. And then this will be also aligned as 16. No, I'm sorry. This is not aligned as 16, sorry. So we put memory argument by 8 byte, and we just pass all of these as 8 byte arguments. And then we put return address, the RBP value, the unspecified variable sizes, and there is this red zone which we don't care about it a lot right now. Yeah, basically like this. And one more thing, and when we write our assembly program, we need to specify sections and global and external functions. So sections are specified with section, and then you put the section name to next of it. You can put any section name, but the linker should know about it. And then there's two keywords here, global and external. And global, well, makes so that the function label you create is preserved, is an actual, what's the name? I don't remember. It's an object on the final .object file, which means that it will be a callable function from an external place. Like when you want, let's say you want to link a library, that's when you create your functions to be external. I mean global, sorry. And when you link them, the linker can find where your function is and call that easily. And there's also this extern keyword, and that's basically what we use when we are using external functions, like C. Let's say we want to use printf in our assembly code. We do extern printf there, so that the assembler knows that we need a printf. We want to print to the variable. Printf function. It can't find it anywhere in the assembly file itself, but it knows that it is somewhere there, so it just passes this as an object link. After we assemble our object files, we need to link them to make the final executable. Most people use LD for this job, and that's what I used to. This is basically just a linker. When linking in Linux, _start function is considered to be our entry point. Just like main function in C. It functions almost the same as main. So when writing an assembly project, we should declare a global start function so the linker can find it and link it to the final executable. So remember when we wrote this function? Let's write this function legally, like how it's supposed to be written. So first, let's get in the foo label. We're gonna push the RBP, which is our first. Sorry. We're just gonna push RBP, last base pointer value, and then we're just gonna move the stack pointer to the base pointer because they're at the same place. We're not using any local variables, and we're going to compare RDI to 0. If it's not equal to else label, we just jump to else label. If it is, we go to increment RSI. And then we're just going to pop whatever's on the stack, which is the previous RBP value. We pop that off the stack and put it on the RBP. And then we're just going to basically return. This is how but as you see, some of these, like, we don't even change RBP and RSP, so these also can be optimized out. This line, and this line is actually not needed. I'm just showing it to show you how to make a proper function. And we're gonna do this example right now. This is the last example of today. And we're gonna make a hello world program in Linux. So we have to understand what a syscall is first. A syscall is what you use to interface with your operating system. Well, when you're, let's say, writing to a file, you don't do that on your own. You tell operating system to do that for you. And the syscalls are, well, there are lots of syscall numbers. You can look at them from internet or unistd64.h. That shows you the syscall numbers and how you use the functions. You can also use unistd.h to look at whatever the functions there are, whatever syscalls functions you can choose. But the two that I'm going to show you today are write and exit. First, write is like a function. You pass the file descriptor, then the buffer, like what you're going to print, the start of your print, and then the number of characters you want to print to that file. And there's also this exit function, the syscall, and you pass in the return value in this to this. So basically, we'll set up how to do the write, and then to the exit. We're gonna exit. So section, we just have to declare a section.text because we're going to write our code. Then we're going to declare our start function as a global function, like this. And then we put our label down and start writing some assembly code. Since that we're using this is our first argument, and we need the syscall number, Linux kernel uses RAX register for our syscall number, which is 1 for 64-bit assembly for write. So we're just going to move 1 to RAX. This is the system call number for write. And then we're just going to move 1 to RDI, which is file descriptor number for std out. And then we're just going to move, let's go to here and let me show you what I did. Okay, we need to have a T here. I made a typo. Section.data. And then the str with basically a label, and this stands for data. Like you just basically reserve a byte to here, like define a byte here, and that would be tccpp. We'll define this byte, and then in here, let's go back here. We move that to our third argument, which is we need to put in RSI, and we put the address in str to RSI. And then we move 5 to RDX because in TCCPP we have 5 letters, so we move that to here. And then we basically do the syscall instruction like this, exactly like this. This will be the same as this. This will write TCCPP to std out, which is console. We'll probably go on console if you don't pipe anything. And then we're going to exit. So we're going to move 60 to RAX. And that's the syscall number for exit. And we're going to move 0 to RDI as our exit number. And then we're just going to syscall and terminate our function. And this is also how you do comments on assembly. I forgot to mention this. I'm sorry. And this was my presentation. Thank you for joining me with my talk. I'm gonna do a Q&A session right now for 15 minutes or so. If you have any questions, please drop in the chat or TCCP chat in the server. I'll be waiting for 5 minutes here. If you don't get anything, I'll close this thing. Yeah, there's no questions? Should I terminate the stream? I close the stream. I'm looking through the Discord and what? How would that work? All right. So Windows system calls are well. How can I describe this? Mm, um. Well, Windows is like it looks like a functions like they're similar, but uh, okay, my brain stopped. Sorry. They yeah, as an exactly. As I explained it better than I can. Yeah, they're basically like stuck together. So you call them like functions. It's weird. Yeah, I said it better than I can. Yeah. You can also use Win API for that too. Okay, let me go back to the here. That's why most people actually don't like to use assembly under Windows. There's some undocumented stuff, and it's just easier to, and it's more transparent in Linux, so it's easier to understand. Like easier to understand, easier to get it working, easier to make something work, and you don't have that many layers between you and the hardware in Linux. Is there any other questions? Should I close the stream? I don't know what to do at this point. What are you watching? Just a Q&A. Why is stack so important? Alright, so stack is where basically you keep almost all of your variables, all your local variables and stuff. And it is one of the most complicated things to learn in assembly, in my opinion, after heap. So you basically all functions have their own. Like you can't give all functions a global scope for their variables, because they also have to change every time you call the function. There's parameter passing, there's parameter taking, and basically all like function changes and functions itself almost all the time operate on stack. You pass the arguments there, you do your operations there, your local variables are there. Well, everything's on stack basically. It is one of the best ways to keep the data. It's the best, not one of the, it's the best way to keep data there. If no one else has any other questions, I'll close the stream at exactly 1 hour here, because for obvious reasons. Okay. Uh, I'll close the stream at 1 hour exactly now. It should be over now. Let's go.